All right. Welcome. Let's keep this on top. So today is the 1st of March, the 1st of Mechanical March, which means it's all about systems programming languages on Exercism, among which Rust, which is my favorite language, and I'm going to talk about that today. Do make sure to put your questions in the chat during the stream. I'm going to keep an eye on that. All right, first of all, I'm going to be streaming every Wednesday evening throughout March at 7 p.m. Central European Time. That is 6 p.m. UTC. And as you may know, Exercism is suggesting 5 specific exercises to tackle on Exercism, which are particularly well suited to explore systems programming languages. And that's what I'm going to do during the stream, like the main thing. I'm going to go through all of these 5 exercises with you. That means if you want to solve them first, do go ahead and do that first before you watch the stream. This is going to be recorded and posted to YouTube as well, I think. Yeah. The exercise for today is going to be Sieve. Let's open the tab because I'm not even going to try to pronounce his name. Right, so this is the exercise Sieve, and it is specifically about the algorithm. Well, this one right here. Not going to pronounce his name. Yeah, that's what we're going to do today. Solve this exercise together. Because this is the first stream, I want to start off with a little introduction about Rust. I'm not going to talk too much. There are plenty of other videos you can watch if you want to learn more about the language itself. And I'm also going to go through how to set up your local development environment to make sure you get off on the right foot while learning Rust. Right, for the short introduction about the language, Rust, it's a systems programming language. It's been released, 1.0 has been released in 2015, so it's a pretty new language. And so the 3 standout things about the language that I would say is that it's got first-class tooling. So that includes, it has an official package manager, an official linter, an official code formatter. All of these things are really fantastic tools. Older languages have developed these tools as well, but they're kind of scattered across the ecosystem. For example, if you know JavaScript and the Node ecosystem, it can be a little bit of a pain to get all of your tooling to work together well. In Rust, and for example, Go as well, right? I think Go was maybe the first language that really made the tooling around the language itself a first-class citizen, a first-class concern of the language designers, and Rust is going with that as well. Now the second thing is it's got a really fantastic type system. It borrows a lot from functional programming languages. If you participated in Functional February, you may have already experienced one of those functional languages. Now Elixir specifically, I tried out Elixir in February, and it's dynamically typed, right? So it doesn't have a static type system, and Rust borrows a lot of the features that were, let's say, pioneered by statically typed functional programming languages. The one that I'm mostly familiar with is Haskell, which is great, and a lot of fantastic features of Haskell are also in Rust, which I love. maybe the most important example of that would be that there are no like null pointers in safe Rust. Rust has an option type, some and none, which forces the programmer to check for any null values, so you don't get any unexpected seg faults and panicking and nil pointer exceptions and whatnot. So that's a really great support of the type system. And the third thing to mention, really big thing about performance, Rust does not have a garbage collector, but it is still memory safe, right? So if you think about garbage collection, almost every programming language, modern one, widely adopted one, has a garbage collector. The main reason for that is it makes it easier for the programmer, but also it gives you memory safety, right? The two main programming languages that actually don't have a garbage collector, the two main ones people usually think of would be C and C++. And famously, these two languages are not memory safe, meaning it's very easy for the program to make mistakes that lead to memory safety issues, which can be very critical bugs. So Rust is pretty much the first programming language that has, achieved popular adoption. There is a research language, I think it's called Cyclone, that came before Rust, which had a similar system of memory management. But Rust is really the first one that people know about. The first one you can really use productively. So how does Rust do it? Memory safety without a garbage collector. The concept is called the borrow checker, and essentially it tracks ownership of all the values and specifically memory allocations. It tracks that across your code, and this allows Rust to ensure, guarantee at compile time that any memory you allocate is going to be freed and you're not accessing memory accidentally that you have freed before. And part of that is the pattern that people using C++ will already know, which is called resource acquisition is initialization, RAII. In C++, this is just a feature you can use. In Rust, this is the whole language is about that, and the compiler checks that you're not making any mistakes with that. And this allows Rust to kind of allows the programmer to have their cake and eat it too, right? Have the maximum performance of C, C++, while at the same time, being memory safe and protecting the programmer from silly bugs, and not just silly bugs, right? Security critical bugs as well. So that was a little short introduction to Rust. Why did I become interested in it? So the reason I started learning Rust was I I noticed Stack Overflow surveys. Um, they have a ranking of most loved and dreaded languages, right? And I think at this point it's 7 years in a row that Rust has been the most loved language on Stack Overflow, which did make me scratch my head because I also remember way back in university, my systems programming professor telling us that Rust, in his opinion, may be the first serious candidate to replace C, so to speak. At the time, I had no idea what that man was talking about, but a few years later, after I saw these Stack Overflow surveys, I remembered that. So, and I had to ask myself, like, how is this possible, right? This high performance systems programming language. Usually, these are very difficult languages to use. How could such a language be the most loved language for 7 years in a row? So I started to learn, and I loved it. I absolutely loved it. All right, so A lot of you are probably just getting started with learning Rust. If you're participating in Mechanical March and using that to learn Rust for the first time, I just want to give you a little bit of a tip about how to learn Rust. Of course, as a systems programming language, it is difficult to learn. It's not an easy language to learn, although I would say it's very enjoyable. And there is a lot of great tooling and educational material. The first and foremost I would recommend to anyone is the book. There is an official book of the Rust project, which is meant to teach the language. So if you go to rust-lang.org and you click on Learn right up here, the first thing basically that pops up is read the book. If you click on that, you get a lovely ebook here um, with just absolutely fantastic content. Now, I do not recommend to just only do the exercises on exercism because I do expect that you will get stuck very quickly and not know where to go from there. Like, my basic recommendation of how to learn Rust would be to pick an exercise, try to solve it, and if you can't solve it, read the book. Read as much of the book as you need to read until you know enough to solve the exercise, and then stop reading the book, right? It's There's no use in reading the book, reading the content if you don't know what you're going to need these features for. So if you start with the first exercise, you might immediately notice, oh my God, I need to understand the basic data types. Um, that would be 3.2, chapter 3.2. And yeah, at some point you're probably going to need a vector. I think vectors, yeah, common collections, that's already in chapter 8. So at the beginning, you might have to plow through a whole bunch of chapters to really get the basics down. If you want to work with vectors, that's already chapter 8. And we're actually going to do that today. So yeah. Oh, and I definitely recommend checking out chapter 6, enums and pattern matching. Really a standout feature of the language. So that was a little bit about how I recommend to learn the language. Let's talk about how to set up your local development environment. Because why do I even want to talk about this? The reason is simple. So I'm gonna open up an exercise that I haven't solved yet. Exercism has this great online editor, right? So if you wanted to just get going, you could just jump in here in the online editor and declare a variable, give that a number, and maybe you want to reassign that variable to another number, and you just get started coding like this. And if you think you're done, you might run the tests. Now, I don't recommend you do this because it's not the best developer experience. Um, these two lines to a lot of programmers might seem like very benign, looks correct, there's nothing wrong with this. However, there's already a mistake, and the online editor is not telling us about this mistake. Specifically, the variable x. In Rust, every variable is immutable by default, meaning you cannot reassign, you cannot change the value of that variable. So the line 5 right here, this is a mistake. I might have to zoom in a little bit more because this looks a little bit small on the screen. All right, yeah, that seems a bit better. So line 5 right here, this is a mistake. We're reassigning to a variable that is immutable by default, and the solution for that would be to put the mut keyword in front of the variable declaration. Now, this is the reason I do not recommend starting with the online editor, because we can do better than this from a developer experience perspective. So I'm in Visual Studio Code right now. I'm going to show you the steps of how to set up Visual Studio Code because it's a very popular, if not the most popular editor. If you're using another editor, feel free to, look up the specific steps that I'm showing right now, how to do them in your own editor. Let's look at the extensions first. The basic extension to get basic language support P in Visual Studio Code would be right this. It's called Rust Analyzer. So you definitely want to install that one. And just a quick heads up, if you search for simply Rust, there is a deprecated extension, but it is marked as such at this point, so you're probably not going to accidentally install this. Just make sure you do install Rust Analyzer. It is also official at this point. Rust Analyzer used to be a separate project, and it was really good, so it got merged into the official Rust project on GitHub, basically. So that is the basic language support. And the second extension I wanted to show you is Code LLDB. This one you're going to need to debug your Rust applications, which you're definitely going to want to do if you're just getting started. I think this is like a generic extension for almost any programming language that is LLVM based. You can see it here, C++, Rust, and a couple more. I think Julia, for example, also based on LLVM, so that one works for Julia as well. So that's basic language support and debugging. And if we quickly look at where are we right here? So should I show you this? Right. Well, if you look at this folder right here, this is a project generated by Cargo, and the cargo.toml is the manifest, the project manifest. It's got just a little bit of metadata about your project in here, and the format of that is toml. So a little I also like to add for Rust is even better toml, which gives great syntax highlighting for toml files, but that last one is not terribly important. The first two ones are language support, LSP, and debugging with Rust Analyzer and Code LLDB. And also, what I definitely recommend, especially for Visual Studio Code, I don't know how it is in other editors. If we hop into the settings real quick and we search for Rust Analyzer check command. So this setting right here, Rust Analyzer check command, this is going to determine which command Rust Analyzer is going to use to check your source code. And by default, this is just check, which means it's basically going to run the standard compiler over your code. However, what I highly strongly recommend is you change this to Clippy. Clippy is the name of Rust's official linter. It's really fantastic. It's got a lot of great lints, and almost every lint has educational descriptions of what's wrong almost. So definitely always read Clippy warnings very thoroughly. You'll learn a lot from that, especially at the beginning. So just to demonstrate our setup here real quick, before in the online editor, we declared a variable x to have the value 42, and then we reassigned that to the value 24. And we're already getting a few more errors. One warning is that we're not using the variable x. So let's just use that down here real quick. And here we're getting an error. And a very helpful compiler error message, which saying cannot assign twice to immutable variable x. So that's exactly the error that we wanted to get. And if you look closely, it's actually telling us what we need to do to fix this, right? It's saying here, consider making this binding mutable by writing in front of x. So if we do that, the error will go away. And the only warning that remains is the fact that we're not using this value, 42 right here, right? We're setting the value to 42 and immediately overriding it, so we're not even using this, and we're being warned about that. I also wanted to make it just a little example of a lint that is going to be caught by Clippy, but not by the standard compiler warnings, right? So let's say we make a little if statement, and we're comparing x to true here. Those of you who are familiar with if statements will already know what's wrong with this. X is already a Boolean. Comparing a Boolean to another Boolean, especially comparing to true, is basically useless. And Clippy is telling us as much, right? Equality checks against true are unnecessary. And also, when you're getting these linter warnings, do check if there is actually a quick fix available. So you can quick fix this, and it's going to fix that for you. This one is very easy to quick fix, but there are a couple of other quick fixes that are actually kind of impressive. Like, I'm always impressed with how much Clippy can actually fix automatically for you. And the keyboard shortcut for that is Control Dot, and then just hit Enter to let Clippy fix your code for you. So this is looking pretty good. And yeah, I also wanted to say a little bit about working locally with Exercism. So if, let's say you've never you've never solved any Exercism exercises before, or you have only done so in the online editor, right? Didn't want to open a terminal. So if you until now have only used the online editor, I'm just going to point you very quickly to the documentation that explains how to work locally with Exercism, because there is a CLI tool. If you Google search for Exercism CLI walkthrough, this is already the walkthrough. This is the documentation, which also links to the walkthrough, right? Here's the documentation, and I recommend going through this. It explains everything about how to get the CLI, which is called Exercism. So you will have a command Exercism available in your terminal, and it explains how to use that to solve exercises locally. So I just recommend going through that, and the installation of the CLI actually has a really nice like walkthrough wizard kind of thing, right? So it's just telling me to install from source, but Fedora actually has the Exercism CLI in the standard repositories, so make sure to check the standard repos of your distribution if you're working with Linux. I think that's everything for the setup. At this point, we should be able to get started on the exercise. Again, do feel free to post any questions you have about Rust, the history, Exercism, whatever. Post that in the chat. I'm happy to take the conversation any direction that you like. So let's look at this exercise. Well, what we have to do in this exercise is essentially find all of the prime numbers up to a given number. argument to a function. And the exercise is also telling us to use a very specific algorithm. This is not going to be checked by the tests. However, we do want to do it properly and use this algorithm. If you're already familiar with this one, that's great. And I'm not going to go too deep into this. If you look at the graphic's pretty good about explaining it. So what we're basically doing is we're creating an array like of all the numbers all the numbers up to a given limit. Let's just quickly hop back into the exercise here. You will already have this function stub, and the upper bound, like the maximum number, the highest possible prime number, is actually given as an argument to this function. So we have a limit for the prime numbers that we're looking for. The algorithm works such that you're creating an array up to this bound, and you're going through each number. And if it is a prime number, you mark all of the multiples of that number as not a prime number, right? So you would start at 2, 2 is the first prime number, and you mark all of the multiples of 2 as not prime. These are marked as red here, right? 4, 6, 8, 10, 12, and so on. Then we go to the next number. 3 is also prime, mark all of the multiples not prime. And then we come to 4. 4 has previously been marked as not a prime number because it's a multiple of 2, and therefore we skip that one. And we go right to number 5 and continue to mark all of the multiples of 5 as not a prime number. So that's the basics of this algorithm. Let's go ahead and try to implement that. So what we need first is an array with the length of this upper bound right here. So let's declare a variable with the keyword let. Maybe we'll just call this array. No, I wanted to call this Sieve because this is our Sieve. And let's create an array. True of length upper bound. So we are already getting an error here. However, this is the correct syntax to declare an array of size upper bound number of elements, and pre-fill the array with the default value of true. Now, why are we getting this error here? The error is saying attempt to use a non-constant value in a constant. So if you don't know this error message, it might not be immediately clear, but essentially arrays in Rust have to be, the size of the array has to be known at compile time. It must be statically sized, so to speak. The reason for this is that arrays in Rust are always allocated on the stack. As you know, Rust is a systems programming language, and therefore it is very much concerned with allocations. Is memory allocated on the stack? Is it allocated on the heap? The stack is very efficient. The heap, on the other hand, is very flexible and dynamic, although you sacrifice a little bit of performance when you're using the heap. So in Rust in general, you always have to be very explicit about doing heap allocations because it does have a certain performance impact. And the size of this array, about the stack allocations, right? Stack allocations work in such a way that every function always gets the same size of memory, the same amount of memory on the stack. That size must be known at compile time in order for the compiler to do its thing. And this is the problem that we're having right here, right? The compiler doesn't know how large this array is, so it wouldn't know how to fit this function on the stack statically at compile time. That's why we're getting an error here. This function at runtime can be called with different values of upper bound. It could be called with 10, it could be called with 100. And because of that, this array can have different sizes at runtime. So what we need to do, this we have discovered is wrong. What we need to do is we need a dynamically sized array, and the name for this type in Rust is the same as C++. This is called a vector, right? So let's declare the variable sieve, and vec is short for vector, and that type has an associated function new, which is used to create a new vector. Now at this point we're getting an error because Rust doesn't know what is the type of the actual element of this vector. And we could tell this to Rust right now, right? We could say, oh, this is a vector of, Booleans. But we actually don't need to do that because in most situations, Rust can infer the types of your variables. You just have to use them at least once, and Rust will be able to figure it out. So, for example, let's say we want to put the value true on this heap, we would use the push function. Now, again, we're getting the same error as before. Pushing is mutating this vector. It's changing its value. Therefore, the variable sieve must be mutable. And we're getting another warning, but we're not getting a warning anymore about the type annotations, right? So actually, if you hover over the variable, you can see in this pop-up that Rust correctly infers the type of sieve as a vector of Booleans. So, oh yeah, this is already telling us the correct thing. I wanted to a bit later, but is this Clippy? Yeah, this is Clippy. It's already telling us to do. I do want to make a few more mistakes first with you guys. So the next thing we want to do is we want to have a specific number of values true, right? I think I haven't said this, but the reason we're filling the vector with true is because at the beginning, every number is marked as prime, and throughout the algorithm, while we're going through the array, the vector, we are continuously marking each number as not prime. So we're starting with all elements set to true. Now there's also a function in the standard library to set a given number, like to resize the array. That's actually the name of the method right here. We can resize it with a new length. We're going to say the length of this vector should be upper bound, and then we need to specify which value this should have. And now we're getting an interesting error. This one we actually need to fix, and I think I want to fix that right now. So the error message is mismatch types, right? Expected type usize and found type u64. So what's this about? The data types, like these basic primitive data types, that's part of chapter 3 in the Rust book. So you will get to learn about. Let me just say that the u, this is an unsigned integer. So only positive integer numbers can be expressed with u64. And the 64 stands for the size, the number of bits, right? So this is a 64-bit unsigned integer, and usize, I think in C, C++, the equivalent of that would be size t. This is the size of a pointer of the target platform. Now, it's very likely that if you're on a desktop or a laptop, even if you're a phone, right? Even phones these days are usually running 64-bit processors, and definitely all laptops in laptops and desktops for many years have been using 64-bit architectures, which means that in our case, usize and use64 are actually like the same size and that is why we can safely redeclare upper bound as usize, right? I never knew the difference between type casting and type coercion. So I don't know if this is a cast or a coercion. This is basically just, transforming the type U64 to usize, and because the size of these types is actually the same on our target platform, there's not going to be any bugs, right? So on a different architecture, let's imagine for a second we are on an architecture with 32-bit pointers, a 32-bit architecture, upper bound size in such a situation, and U64 value actually has a larger value that can be expressed with 32 bits. The maximum number of 32 bits should be about 4 billion, right? This variable, this value is larger. It would be truncated here, and that will probably result in a bug. However, in our case, the sizes of these integers is the same, so we don't need to worry about that. Now, you may also wonder, why are we not getting error messages here? I am reassigning this variable, right? But upper bound is not declared as mutable. This is actually, we're using the let keyword here again, which means this is not reassigning the same variable, but we are shadowing the previous variable with a new variable declaration. This may seem like nitpicking to you, but if you go into the details, the bugs that are often caused by mutable variables, the reason these bugs appear, they actually cannot, these bugs cannot be caused if you use shadowing and a redeclaration of a new variable. So this is pretty safe. However, we could also have declared this parameter, this function argument is immutable, and then reassigned it here. So that would have worked. Oh no, it doesn't work. Thank you, compiler. All right, the compiler is correcting me right on the spot, right? Reassignment with mutability only works if the types. However, redeclaration and shadowing of previous variables actually works with a different. So this variable is of type usize, this variable this is usize, and the compiler is completely okay with that. Now, why did we even have to do this, right? We had a type error here. Upper bound was U64, but a usize was expected. If we hover over resize, we're seeing the function signature of resize right here. And it's saying that the new length, the expected type here is usize. And this is simply because, just like in C, C++, sizes, lengths, and are expressed as the size, this specific type, right? Usize. Also, if you are on a vector, if you call the function length, the return value of that is also going to have the type usize, right? So anytime you're working with sizes, with lengths, it's going to have the type usize. All right. So this is looking pretty good, but we got a warning from Clippy previously, and it gave us a very good suggestion, namely that if we recall, this was how we declared the array, right? And there is a macro in the array that you can use basically the same syntax to create a vector, right? So this is a macro. It looks almost like a function call, but the way to distinguish functions from macros is with these exclamation mark, right? Macros, I'm not going to go into macros right now, right? It's kind of a preprocessor, but the macros are hygienic. This is a very advanced feature. I think the Rust book has 20 chapters, and I believe that's part of chapter 19. So don't worry too much. It's maybe a preprocessor, a safe version of a C preprocessor. Maybe you already know a language that does have macros itself. Nim has macros. I think Elixir has macros too, right? If you did Elixir last month, I did Elixir, but I didn't do any macros. I guess in any language that's going to be an advanced feature. All right. And there is a little bit of a mistake right here that I'm also going to fix right now. I want to be able to index into this vector sieve with like the specific number that I want to find out, is this a prime or not? And we also need to check if upper bound is a prime. However, if we create a vector of size upper bound, the maximum index is going to be upper bound -1, right? Because indexes start at 0. So in order to be able to use upper bound itself as an index into this array, we're going to just make it 1 element longer. And just for completeness sake, we also have indexes 0 and 1 at this point, but we don't care about these because 0 and 1 are not prime numbers. So let's set these to false right now. Is there an advantage to using this macro over the previous declaration you typed out? Not really. I think there is a very, very small advantage. Um, let's get rid of this array here. We are not going to need this anymore. So let's say we do this again. We create a vector like this. And what did I use? I used the function sieve.resize, nope, not reserve, resize, upper bound, and true, right? This is what we wrote. This is a tiny, slightly, little bit less efficient. The reason is that this function call right here is already making a heap allocation. The standard size of an empty vector is 4. I think it's they just made measurements and measured which is the best default size for an empty vector to get the best performance on average. So this is gonna heap allocate enough space for 4 elements. And this function call right here, if upper bound is greater than 4, this call resize is going to have to make a new heap allocation under the hood, which means this is more than likely going to result in 2 heap allocations. However, this macro right here, I'm pretty sure this is going to ensure that only 1 heap allocation is going to be made right at the start. We could have done this ourselves. There is a function with capacity. It creates a vector, an empty vector, 0 elements. However, the underlying allocation of memory on the heap is already going to have enough capacity to store enough elements, as many elements as you're specifying here in this argument. So if we wrote it like this, performance-wise, it would be pretty much the same. apart from performance, which we can fix manually, the macro is just a little bit shorter, nicer to read. If you prefer to not use macros for some reason, you can get the same performance with the manual version, the plain function calls. All right. So what are we doing here? Let's just maybe I jumped the gun here a little bit, right? So the easy way to do the simple naive way would be to set the element 0 to false and then set the element 1 to false. However, we can write this on a single line by using tuples, right? So these parentheses are creating a tuple with 2 elements, and then we're just assigning to that another tuple with the 2 variables false. So I think at this point we have initialized our sieve correctly, and we can start implementing the algorithm. So we have to iterate first over all the numbers. And how would you do iteration, right? If you're coming from a C-like language, maybe C itself, maybe Java, maybe JavaScript, a common syntax for loops is something like this, right? Let's try to make this syntax rusty. We use let to declare a new variable. We start at the index 0. Maybe we start at the index 2, right? Because we can skip over the numbers 0 and 1. And we want to iterate as long as our index I is smaller than sieve.len. And we're just going to increment I, something like this, right? This is the C-style syntax to write for loops iterating over an array. The syntax does not work in Rust. So if you want to do something like this, there is a nicer syntax. In my opinion, it's nicer. What we're going to do here is, and essentially, I hope we're going to have time to cover this. I'm looking at the time, we're already far into the stream. I got to speed up a little bit. So we might not be able to cover like iterators in its totality, but essentially the syntax is going to be 0 of, this is a range, right? We're going to go to upper bound plus 1. This is going to be the last index, right? Wait, I think this is incorrect. Yes. So this is an exclusive range, meaning the last element of this range is not going to be included. If you write it like this, upper bound is going to be excluded from the range, but there is also an inclusive range with the equal sign right here, which means upper bound is going to be included in the range. So this way we can iterate over the indexes into Sieve. And if you recall the algorithm, at first we have to check, if this element in the Sieve is actually a prime. And we've already stored this as a Boolean. If this is a prime, then we are actually going to do something. So I'm going to say right here, if it's not a prime, we're just going to continue, right, with the next element of the array. So at this point, we know that I, our number I, is actually a prime number. And what we have to do next is to mark all of the multiples of I as not prime. So let's do another loop with conventionally another like very well named variable j. And what is the range that we need to iterate over here, right? We kind of need to start at I, not really, right? So let's say 2 is a prime number. We don't want to mark 2 as not prime. So let's say we add another I, let's say we double that. So that would be the next multiple of I. We start with that, and then I guess we iterate to upper bound. However, this would essentially like mark all of the numbers after that, mark them all as not prime, which we also don't want to do. So what we want to do is take steps of a specific size, right? And this range syntax here, this creates a type range. Like this is not even just a specific syntax to for loops. You can declare some variable foo and set that to this value. We don't have any variable I is not declared here, but if you check that, this is just a regular type, right? Range inclusive. You can do whatever you want with this. And it turns out this is an iterator. And iterators, um, an iterator is just an interface, a trait in Rust. We might have time on another stream to go into depth about iterators, but it's basically Rust's way of expressing, iteration, sequence, iterating over collections, over all the elements of a collection. Um, so you can imagine all of these numbers in this range as a collection, and the syntax is getting us an iterator over these numbers. And iterators have a method steps. It doesn't. I think I need to wrap this in parentheses because otherwise, if I just put the dot here, it's a method on upper bound, which is of type usize, not type integer. And here, there we go. We have a method called stepI, and we can say like how many steps at a time do we want to take. And in order to get all of the multiples of I, we probably want to step by I. At this point, we are iterating with the variable j over all of the multiples of I, and we can simply set these variables to false, right? So we're marking them as not prime. And now we have at the right here, we should have like a correct sieve, but what do we need to return? So let's just try to return that for now. Tests are not going to pass if we return this and try to run. It's giving us mismatched types. All right, so sieve is of type Boolean, not of type U64. Okay, so we can't test this. We cannot even test this. Run the tests on this. But I can tell you what the problem is. Now we have a vector of booleans, true and false, but we actually need to return a vector of the actual primes, like 2, 3, 5, 7, and so forth, up to this limit. So let's quickly talk about how we can convert this vector of booleans into a vector of the actual primes. And this time we're not going to use for loops. We're mainly going to use iterators and iterator adapters. So Sieve is a vector, and on vectors you can call into iterator, which means the vector is going to be consumed. You're not going to have access to this vector afterwards anymore. And you're taking ownership of all the elements. So we're iterating over all of these booleans, and we want to basically filter out. And if you know functional programming, you might already know this function. It's a common name in functional programming basically to filter values that fulfill a specific condition. Now, if we just filter this out, x is a Boolean right now, right? We could just filter out the true values, but at this point, we just have an iterator over values true, but we don't actually know what the primes are. So we also need to remember the index of these elements in the vector, and the iterator method for that is going to be enumerate. Enumerate, you can call in any iterator, and it's just going to, in addition to the element itself, give you the index. The index at which it was iterated over. So if we now look at x, it doesn't have the type. Previously, it just had the type bool. Now it has usize and bool. The first element of this tuple usize is going to be our index. So we should actually be able to destructure this right here and say this is prime, right? Seems like a good name. So we're just filtering all of the elements that are prime. And at the end of the day, we want to, now that we have filtered, the actual elements that we need is not tuples of usize and is prime, but it's going to be u64, right? And in order to transform the values of the iterators, we can use the map function. It's also something from functional programming. Oh, this pop-up is getting in my way. And let's say this is the index, right? This is the index. And we don't care about the Boolean at this point because we know this is true. And we are going to map this to just the value of the index. However, if you remember, indexes have type usize, and what we need to return is u64. So in addition to like extracting the value that we need out of this tuple, we're also going to cast that as u64. If you remember, we are on a 64-bit machine, so this casting is not going to cause us any trouble. Now we have an iterator over all of the primes, but we don't need to return an iterator, we need to return a vector. And there's a very handy method on iterators called collect. It doesn't just let you collect into vectors, you can actually collect into any collection that you like. The reason we don't need to specify that we want to collect into a vector is simply because Rust is able to infer this type. We are specifying that we want to return a vector, and this is the last expression of the function. We don't, in other languages, you would have to write return here, right? And I think Clippy is actually going to tell us you don't need to do this, right? And we can quick fix this. So in Rust, you can just write the return value as the last expression of the function. So the Rust compiler can basically figure out this is the last expression, and we need to return a vector. Therefore, I'm going to collect into a vector. If in some case you need to specify a different collection, for example, let's say hash set of u64, you can do it like so, but the syntax is a little bit gnarly. Maybe don't try to remember this right now. And in a lot of cases, it's actually not necessary. So let's see if I've made any mistakes. Let's run. And as we can see, the tests are passing. So we did solve the exercise correctly. We are getting a warning. Yes, I imported the type hash set for this little demonstration. We don't need that anymore. So as you can see, this is one way to solve the exercise Sieve in Rust. We have looked at like regular for loops that you may know from other systems programming languages, C-style languages. And we've also seen that we can do a lot of powerful iteration without any for loops by using these iterator adapters. And a lot of these functions are inspired by functional programming languages. And that's a really great feature that most people who get started with Rust very much do enjoy. So now that we've solved the exercise, and it's actually perfectly 8 p.m., so that is 1 hour of the stream, I'm gonna end it right there. If you enjoyed this stream, do make sure to come back next week, Wednesday evening, 7 p.m. Central European Time. And let me think, what is going to be the next exercise? I actually cannot remember. It's another one with iteration, so it shouldn't be too hard. Let me just check that. Oh, I know where I wrote that down, so it shouldn't take too long. That is the second stream, and I chose to stream the exercise. I cannot find it. No, it's gotta be somewhere. All right, I can't find it. Whatever. Next time we're gonna look at another exercise, one of the five suggested exercises for systems programming languages. It's not pangram. It's not allergies. It's another one about. It's another one about iteration. I think they should have the list on Exercism, right? The list of the 5 exercises. Let's just go on the Exercism webpage. They should have it here. There we go. Right. Okay. Binary search. Okay, it's going to be binary search. Next week, we're going to look at binary search if you want to solve that first yourself before we discuss in the stream. Do make sure to do that and hope to see you guys next time. Have a good night.